Hello everyone, let's discuss conformal mappings. First, let's give some motivation for why we might need conformal mappings. All examples so far that we have done have involved simple boundaries, either plain walls or circles. We now try to develop a method for dealing with more general boundaries. Consider the mapping of a region of the z-plane, where z is equal to x plus iy, onto the lowercase z-plane by the transformation that lowercase z is equal to capital F of capital Z. Hence, let's define a conformal mapping. If capital F of capital Z is an analytic function of capital Z, then the mapping lowercase z equal capital F of capital Z is said to be conformal at all points where the derivative of capital F of capital Z is not equal to 0. Now, let's state some properties of conformal mappings. An interesting property of conformal mappings is that capital F conserves the angle of intersection of two curves intersecting at capital Z is equal to capital Z0, where the derivative of capital Z0 is not equal to 0. To prove this, consider 3 points P, Q, R in the capital Z plane, represented by the numbers ZP, ZQ, ZR. We want to write ZQ is equal to ZP plus delta e to the I alpha, and ZR is equal to ZP plus epsilon e to the I beta. The angle between the straight lines PQ and PR is beta minus alpha. We then consider the images P-Q-R' of these points in the lowercase z plane, represented by the complex numbers lowercase zp, lowercase zq, and lowercase zr. When delta and epsilon are small, we can approximate lowercase zq and lowercase zr using a Taylor series and get that zr minus zp divided by zq minus zp is equal to epsilon over delta e to the I beta minus alpha. Hence, the angle between the lines P-R' and P-Q' is still beta minus alpha. A consequence of this result is that smooth lines in the capital Z plane, which do not pass through a point at which f' of z is equal to 0, stay smooth in the lowercase z plane. However, a curve which passes through z0, where capital F' of z0 is equal to 0, may have a sharp angle at lowercase z0 is equal to capital F of capital Z0. Next, let's consider an application of conformal mappings to simple fluid flows. If W equals f of z, which is a complex potential for a flow in the lowercase z plane with velocity uv, then F equaling f of capital Z gives a possible flow in the capital Z plane with velocity components capital U, capital V. So now let's discuss the general approach. Given a complicated geometry in the capital Z plane, find a mapping lowercase z is equal to capital F of capital Z, which gives us simpler geometry in the lowercase z plane. Find the complex potential in the lowercase z plane, W equals f of z. Hence, obtain complex potential in the capital Z plane with W equal to lowercase f of capital Z. The velocity in the capital Z plane is then given by the chain rule such that u minus iv is equal to dw over dz, which is equal to df over dz times dz over capital GZ. Then let's talk about mapping circles. Consider the transformation z is equal to f of capital Z, which is equal to capital Z plus a squared over capital Z, where a is real. Since f' of capital Z is equal to 1 minus a squared over z squared, the mapping is conformal except at capital Z is equal to plus or minus a. We now consider the image of the circle, radius a. Capital Z is equal to a e to the I theta, z is equal to a e to the I theta plus e to the minus I theta, which is equal to 2a cos theta. Hence, the circle is mapped to a straight line y equals 0, x is between minus 2a and positive 2a, with the exterior of the circle mapping to the exterior of the line section minus 2a to 2a. Note that the line minus 2a to 2a in the capital Z plane is in fact a branch cut, since capital Z is equal to a half lowercase z plus or minus lowercase z squared minus 4a squared. So the images of B and D in the lowercase z plane are different points lying either side of the branch cut. Uniform flow past the flat plate parallel to it is given by W is equal to uz. The corresponding flow past the cylinder is W equals U capital Z plus a squared over capital Z, which is the flow we already have considered. However, we can look at this problem the other way around and consider the flow at an angle to the circle in the capital Z plane and see what the corresponding flow is in the lowercase z plane. And as ever, thank you for watching.